Fluoroantimonic acid is 10 quadrillion times stronger than 100% pure sulfuric acid. This substance represents the absolute limit of acidity currently achievable in a laboratory environment, surpassing any naturally occurring corrosive agent. On the Hammett acidity scale, this superacid reaches a value of -28. For context, the scale for standard acids usually bottoms out at -12, making this liquid 16 orders of magnitude more potent. The acid is synthesized by mixing hydrogen fluoride with antimony pentafluoride. This combination results in a chemical synergy, where the antimony pentafluoride acts as a powerful Lewis acid, driving the acidity to extreme levels. In the mixture, antimony pentafluoride molecules attack the hydrogen fluoride to capture fluoride ions. This leaves behind highly reactive protons that have virtually no interaction with their environment, effectively existing as naked charge carriers. The released protons immediately associate with secondary hydrogen fluoride molecules to form H2F+ ions, known as fluoronium. These ions are the active species responsible for the system's incredible ability to donate protons. The corresponding anion is the hexafluoroantimonate octahedron. Because this anion is exceptionally large and has its negative charge spread over 6 fluorine atoms, it does not attract the loose protons back, maintaining the high acidity.
Pure hydrogen fluoride undergoes autoprotolysis, but the equilibrium is shifted dramatically by the presence of the Lewis acid. This shift creates a concentration of solvated protons that exceeds any other known solvent system. Fluoroantimonic acid can protonate even inert hydrocarbons like methane. This process forces carbon to form 5 bonds, creating the highly unstable and fleeting methanium ion, which was once thought to be impossible in classical chemistry. This chemistry was pioneered by Nobel laureate George Olah, who used superacids to stabilize carbocations. His work transformed our understanding of organic reaction mechanisms and the behavior of carbon atoms under extreme chemical stress.
Unlike standard acids, fluoroantimonic acid aggressively attacks glass by reacting with silicon dioxide. It breaks the silicon-oxygen bonds to form silicon tetrafluoride gas and water, literally melting through laboratory beakers in seconds. Even noble metals like gold can be dissolved by this acid when an oxidizing agent is present. The extreme proton concentration facilitates the oxidation of metal atoms into soluble ionic complexes that would remain stable in weaker acids. Organic polymers and plastics are rapidly carbonized upon contact. The acid strips protons and cleaves carbon-carbon bonds, reducing complex structures to a charred remains of elemental carbon in an exothermic display of chemical force.
Polytetrafluoroethylene, or Teflon, is one of the few materials that can withstand this acid. The strength of the carbon-fluorine bonds and the dense electron shield of fluorine atoms prevent the acid from accessing the carbon backbone. Due to its reactivity, fluoroantimonic acid must be stored exclusively in containers made of high-quality Teflon. Any trace of moisture or impurities in the container could trigger a catastrophic failure and release of toxic fumes. The acid reacts explosively with water. The hydration of the protons is so exothermic that it causes the mixture to boil instantly, releasing clouds of lethal hydrogen fluoride gas and hydrofluoric acid mist into the surroundings. The hydrogen fluoride gas released during reactions is a potent systemic toxin. It penetrates deep into lung tissue and skin, causing delayed but severe damage by binding to calcium and magnesium ions in the body. In the petrochemical industry, this superacid is used as a catalyst for alkylation and isomerization. It allows for the production of high-octane fuels by rearranging hydrocarbon structures at much lower temperatures than thermal cracking requires. It can break down heavy, long-chain alkanes into smaller, more valuable fragments. The ability to generate carbocations efficiently makes it a key tool in developing new synthetic pathways for high-performance lubricants and specialty chemicals. The acid is a colorless liquid that fumes heavily in moist air. Its density is significantly higher than water, and it exhibits high viscosity due to the extensive network of hydrogen bonding between the hydrogen fluoride molecules. The viscosity arises from the unique structure of the liquid phase, where polyatomic anions and solvated protons form a complex interconnected web. These interactions determine how the acid flows and how it interacts with solid surfaces. Standard pH meters cannot measure superacids because they would be destroyed instantly. Instead, scientists use Hammett indicators, which are weak bases that change color only when they are successfully protonated by an extremely strong acid. The degree of color change in these indicators allows for the precise calculation of the acidity function. By comparing the absorption spectra of the protonated and unprotonated forms, the chemical potential of the protons is determined. The stability of the hexafluoroantimonate system is rooted in the high bond energy of the antimony-fluorine bonds. This thermodynamic stability prevents the anion from breaking down even when subjected to intense heat or high pressure. Magic acid is a similar superacid made from fluorosulfuric acid and antimony pentafluoride. While both are powerful, the fluoroantimonic system is stronger because the hydrogen fluoride solvent is a weaker base than fluorosulfuric acid. Carborane acids are often cited as the strongest solo acids because they can be stored as solids. However, in terms of absolute protonating power in a liquid system, the fluoroantimonic acid mixture remains the undisputed champion. Theoretical studies suggest that superacids can even protonate certain noble gases under extreme conditions. While difficult to achieve, this highlights the immense chemical potential available when protons are decoupled from their traditional solvent shells. By providing an environment with zero nucleophilicity, this acid allows chemists to observe carbonium ions that would normally exist for only a billionth of a second. This effectively freezes these reactive intermediates for spectroscopic study. To visualize the strength, if stomach acid were the height of a small pebble, fluoroantimonic acid would be a mountain range reaching into the stratosphere. The sheer scale of its chemical activity is difficult to comprehend using standard metrics. Working with this substance requires specialized fume hoods and full-body protection made of acid-resistant fluoropolymers. Standard latex or nitrile gloves offer zero protection and would be consumed instantly upon contact with the liquid. Technicians handle the acid inside glove boxes filled with dry nitrogen or argon. This prevents any contact with atmospheric moisture, which is the primary cause of laboratory accidents involving superacids and their precursors. The high vapor pressure of hydrogen fluoride means the acid constantly emits corrosive gas. This gas can etch nearby glassware and corrode stainless steel equipment even without direct liquid contact, necessitating constant air filtration and monitoring. In the event of a spill, neutralization must be handled with extreme caution. Adding a strong base too quickly can cause a massive release of energy. Usually, specialized dry chemical agents are used to absorb and stabilize the acid first. The extreme acidity is fundamentally a result of fluorine's high electronegativity. By pulling electron density away from the antimony and hydrogen atoms, it creates a chemical environment where protons are energetically compelled to leave their host molecules. Within the hexafluoroantimonate ion, bond lengths are shortened due to the high effective nuclear charge of the antimony. This compact structure contributes to the overall stability and non-reactive nature of the resulting salt complex. The coordination number of 6 for antimony is critical. This geometry perfectly balances the steric repulsion of the fluorine atoms while maximizing the electrostatic attraction, creating one of the most stable anions in all of chemistry. The acid facilitates skeletal rearrangements of organic molecules. By forming intermediate carbocations, it allows straight-chain hydrocarbons to transform into branched isomers, which burn more efficiently in internal combustion engines. In industrial alkylation, fluoroantimonic acid promotes the reaction between isobutane and light olefins. The resulting alkylate is a high-purity component of premium gasoline, free of the sulfur and aromatics found in other refining processes. The acid environment allows for the observation of the stability difference between secondary and tertiary carbocations. Under these conditions, the migration of protons and methyl groups can be tracked in real time using nuclear magnetic resonance. Nuclear magnetic resonance spectroscopy of superacid solutions has provided the most detailed maps of molecular structures ever recorded. It reveals the exact position of every atom in ions that exist nowhere else in the universe. When cooled, fluoroantimonic acid can form various crystalline hydrates and salts. These solid phases retain much of the acidic potential and are used in specialized chemical vapor deposition processes for the semiconductor industry. The extreme reactivity is harnessed to etch patterns onto silicon wafers with atomic precision. By controlling the concentration and exposure time, engineers can create nanometer-scale features essential for modern microprocessors and memory chips. Release of fluoroantimonic acid into the environment would be catastrophic. It would not only poison local water sources, but also react with soil minerals to release a variety of other toxic heavy metals and halogenated compounds. Waste acid must be neutralized using a multi-step process involving calcium carbonate or lime. This converts the fluoride into insoluble calcium fluoride, which is chemically inert and can be safely disposed of in specialized landfills. Preparing the antimony pentafluoride precursor is itself a dangerous process, involving the reaction of antimony pentachloride with anhydrous hydrogen fluoride. This step requires precise temperature control to prevent runaway reactions and equipment failure. Total absence of water is the most critical requirement for maintaining the acid's strength. Even a few parts per million of moisture will significantly lower the Hammett acidity value as the protons become trapped in hydronium complexes. In the presence of water, the fluoronium ion is converted to the hydronium ion. Because water is a much stronger base than hydrogen fluoride, it holds on to the proton much more tightly, effectively quenching the superacid's power. The high density of the liquid, roughly 3 times that of water, means that even small volumes are surprisingly heavy. This density must be accounted for in the structural design of storage tanks and transport piping. Valves and seals in acid delivery systems are made from perfluoroelastomers. These materials maintain their flexibility and sealing properties even when exposed to the most aggressive protonating environments, preventing leaks in high-pressure industrial circuits. Fluoroantimonic acid represents the boundary where the distinction between a solvent and a reactant disappears. At this level of acidity, the solvent itself becomes an active participant in the most fundamental steps of chemical transformation. As the strongest known liquid acid, fluoroantimonic acid remains a cornerstone of extreme chemistry. It continues to enable the synthesis of new materials and the exploration of molecular states that define the limits of the periodic table.